you set the oil, right? Okay, so the sleep rate will be calculated depending on the correlation we choose and end up with the Q oil and Q gas for different zones. So we try to match with the total velocity from spinner and also the sleep rate from correlation and the density or the holdup calculated from density. Deviated horizontal well. For example, like this, the flow structure is not simple. You can see the one here, water is blue, oil is red, yellow is gas. So you make something like this. If you are in a highly deviated or horizontal, for example, you run a standard, this is the CFS, continuous spin flow meter, and you have the capacitance of that one. So you might see that you miss the light phase or the gas on the top part of the pipe. So you're measuring phase only. So you miss the oil, you miss the gas, so cannot be used because the whatever the capacitor is reading also heavy phase. So even though we have the correlation, cannot be used. Yeah. So why? Because this one is segregated flow regime. So light phase is at the top, heavy phase at the bottom. So you might be having some different light phase like oil in the middle. So you can see is will be missing the light phase. So what we come up with is multi-probe tools. It's on next. This one is the SAT tool. So the SAT has 6 spinners. So you can see the arm has spinners. So this is 4-string type of arm. But one, you have the spinner on the side. You have 6 spinners. So you see the spinners on the side of the ball spinner. So when the fluid moving in, rotate the spinner and you see the RPS. So you have 6 RPS and you do the spinner calibration 6 times. Yeah, so you do 6 times.
6 times 6.
No, 6 times spinners, right? So you do the slope positive, negative for each different spinner. So if you have 6 slopes, positive slope and 6 negative slopes, 6 thresholds. So that's quite a lot. And yeah, and you might see sometimes the tool can be rotating all the way. Yeah, so can be look up, look down. So you might see the one of the spinner is at the top, maybe moving down. The spinner here is reading oil, etc. So there will be a different holder or different liquid, different fluid. Yeah. What else? Okay, so the position of the probe number 1, you can get it from relative bearing. So relative bearing is very important because you like to know which one is in the gas, which one in the oil, which one in the water. And so that's the multi-probe tools. We call it multi-probe because we have more than one probe. We call it probe, this one, or discrete measurement. So that's the one. We have the gas spinner. So we do the spinner, but we know where the level of water, where the level of oil, where it's coming from at the sensor, which is your density, not density. We don't have the density. We have the electric and optical probe. Yeah, we have electric or optical probe. For example, this one, we run DNR, density radioactive. And we have the centered CFS spinner. So you have a down and up. Which one is down pass? Blue or
Is
brown?
down pass.
Down pass. Should be quick.
Both.
It's one pass down, one pass up.
Both positive.
Yes, both positive.
Mm-hmm.
But one is more positive.
Oh, more positive.
So which one?
Orange.
Yeah, it's not orange, it's blue.
Blue.
You can choose. Higher cable speed, higher RPS.
Density. Oh, I was looking at.
It's don't pass.
Down pass blue. Higher.
Blue is higher RPS or higher cable speed down. So blue is the higher speed than the blue. Makes sense, yeah? Okay, so you can see that one, and you see the blue one is going up and then move down. So if you look at from the bottom, this one is the most bottom, this is the two, and this is the heel. So from the bottom to top, you can see you have some spinner up, it's going up, but it's going down. Is it teething? Maybe not. You don't repeat on the broad one. The broad one is not repeating. So that's why you cannot use the conventional spin. You can see it's moving up, it's 90 degree, it's more than 90 degree, it's moving down. So probably when you are down pass, your spinner CFS is reading on the water, going downhill, which is faster. So this is going downhill faster, and then you start again 90 degree, it's flat. So it's really affected by the trajectory of the horizontal. That's why in the horizontal where we need to have the correct trajectory details. Yeah. So that's why we might not be able to use the CFS. So maximum is here. So whether this is maximum and then it's all TV, no. And also the raw oil. See, raw oil is the minimum, right there. So here, this is DNR, radioactive, the centered one. Can only read whatever into the void in the tube. So above that one, not read. The gas above cannot be read. Or the water below is not be read there. So you can see the blue and red, they are not repeating. You might have some gas here starting moving up the whirlpool. So therefore you pass. This is water, you have some oil, but the other part is just showing all water. So it's not consistent. Yeah. Therefore we cannot use the conventional density and spinner in this type of flow regime. Yeah, this is the capacitance array. So you have 12 line, which is 12 sensors. This is 12 sensors. So 0 means gas, 0.2 is oil, which is the green. Blue one is 1 is water. So you can have 3 phase. Yeah. The capacitance, as I mentioned, you can only have hydrocarbon and water, right? But in the 3-phase condition, it can be used for 3-phase because you have water, oil, gas. So it's separated, segregated. So if the capacitance is here, okay, it's water. If the capacitance here, it's okay between water and oil. Yeah, so when between water and oil, you have the range. This one is oil. If your capacitance here, between oil and gas. If you are here, is the gas. So it can detect the 3-phase because they are segregated. But if they are mixed, we cannot. We just use hydrocarbon and water, so 2-phase. Therefore, you might see the gas here, and you have the oil, and then you have the water. So if you look at the map on the multi-array tool, so you might need to open like that. The middle, the top, the side at the bottom. So like this. So you like to expect the light phase in the middle. And the fastest speed should be in the middle because the gas should be moving if you are in going uphill. But if you're going downhill, maybe not. Something like this. But this one is the hold up, not the speed. This is the hold. So you can see when you're going downhill, you occupy more gas. Yeah. When you're going up, you don't have any gas. So that one is small of gas and going up. So whether the gas is going somewhere or because it's not detected. Yeah, because the tool itself, you have something like an offset. When you see this one, yeah, you see the offset here within the center. The end point and that is you have the offset. So the spinner is not really at the wall. It's just the offset. So you might miss something. You might miss something at the top. So that's the
So but on the lock for spinner, that only two for blue and brown colors.
yeah.
Supposed to be 6, right?
Or in horizontal it's difficult to get because you cannot use the wire line, yeah? You cannot use just the slick line. You need to have convey with other stuff like coil tubing or the tractor.
I mean it's supposed to be have 6 spinner.
Okay.
Cannot. So the reading is one at the top or bottom or
No, you have two passes maybe, just two up passes or two down passes or one up, one down.
so the reading is the average or
What do you mean?
the spinner reading for the brown for example the blue color.
The blue color is for the down pass, right?
Okay.
What is the average?
But it's supposed to be 6 spinner. So it's supposed to be
this one
6
is not CFS.
or CFS only.
Yes.
Not okay.
This one CFS.
Or only one spinner.
Yes.
Oh okay.
Yes. That's why you're not repeated between down and up, for example.
Okay.
Yeah, it's not repeated. That's why, because this one is centered. It might immerse in water, it might see oil, it might see gas, or
So it's not set spinner array tool.
yeah.
No. Okay.
That's why we need to have the array.
Mm.
The array only the cat here at the bottom.
Okay.
Yeah, this is the conventional density radioactive, and this is CFS,
Oh.
the centered.
Oh.
Yeah, you can see the title CFS, not SAT. Yeah. So that's why you have some limitation.
Okay.
It's just to show the limitation. So VM is not measured by the spinner, yeah, because it's not correct. It's not the mixture. Maybe heavy vice only, maybe the middle vessel. Raw M is not hold up with it, yeah. Raw mixture is the center tool, right? So it's either in the water, in oil, cannot be the cause. It's in the center. Facelift inversion, slippage can be negative because it's going downhill. Slippage negative, heavy phase goes faster than light phase. Recirculation, yeah, you might have some recirculation when you are in 90 degrees, for example, like that. So maybe you have some water moving up, but it's not enough velocity to recirculate down traps. You might have something like when you have something like this. So you have the gas is trapped here. So because there are not enough energy to move the gas into the surface, so it's always there. So it can be something like this. So when you see the spinner is just not moving at the top because it's gas not moving. So it can be like that. Or if you have something like this is water in the sun. So water lit up, but some of the water maybe stays there.
Like
So-
toilet bowl. Toilet bowl.
Sorry?
Like toilet bowl.
Thinking too much.
Water trap.
Yeah, so water's in the sun.
Okay.
Water sun. And you need to flush it.
Okay.
Okay. Alright, so that's why it's not giving you the correct input or reading. So that's why we go to multi-probe tools. This one is distributed measurement or a multi-probe or yeah. We have electric bulb, optical capacitance. Yeah, we know that one already, yeah. Electric is based on the, I think I haven't talked about this one, but do we have the, should have this one. Oh, electric, optical, and then the capacitance, and we have spinner or Doppler, but Doppler is not there yet. So that's on the cat. So green is oil, blue is water. This one ENR, yeah. So water, oil, and gas. So you might see, I don't know which one is down, which one is up. Maybe the one who's down here. So it's looking at only water all the way. And when you're moving up, you might see some oil all the way up. So it's not repeating between down and up. But when you have the card, you see this one. This is the cross section at this depth. This cross section at different depth. So you might have some different cross section. You're looking at LMR, it might be. So this one is the small circle is the position of the probe itself. The big one, CWH. So you can combine those because the principle is similar, capacitance. But again, in this case, I don't know, you might be reading just oil, but you might see the changing. Yeah. So you can see the rotation. This is 12. See, the 12 is here, 12 is here, 12 is in the middle. So you might see the tool when it's going up, this is changing. It's rotating while going up or going down. So that's why we need to know where the water level on each different slice, and you can see from the capacitor array. Yeah. You might have gas at the top. So this is the principal electric. All the manufacturer's principle is similar. You have two probe, but two probe is very close itself, maybe just 0.5 millimeters between those two. If you are in water continuous, water is considered conductive. So if it is conductive, then there will be no voltage. It's conductive. The zero signal is zero. So if you have a bubble of oil and stick on one of the probe or electrode, will be disconnect. Yeah. So you have some connection, disconnect. So you have some signals, disconnection. Depend on the bubble versus time. So you can have a small bubble here or droplet they call it in order to disconnect in the water. So bubble oil can be small. It's something like this. So disconnect between those two electrodes. And yeah, this is the open field. It's just like one needle, but actually there are two probes, two electrodes on the side. If you see the red or that, you actually see two needles. But open field is just one. So something like this. This is the red. You have the tool body and you have the probe. So if you are in water, it's connected, so no voltage. But if you disconnect, you will be a voltage. So if bubble pass through one of them, will disconnect in water. You have this one as well, the same. This is the ramp. This is the principle is the same. There are two probes. So you have four probes. This one is 12 probes. Okay. So here are the things. You can have voltage, you can have no voltage. So for example, it's conductive. In the water is conductive, yeah? Conductive. So this one is high voltage. So it's conductive, then we have voltage. Yeah. But if you have some oil bubble, it's disconnect. You have some disconnection. So you need to put some threshold, then we have some disconnection. So you have the blue is water, the white one is not water. So it can be only these two, yeah? Conductive and non-conductive. So can only be used for water and non-water. If you are dominated in non-water, oil for example, in the oil it's disconnect because it's non-conductive, isolated oil. But you have some water bubble. The water bubble has to be big enough to connect those two. Yeah, should be bubbles big enough, maybe just 1 millimeter is okay. So you have water bubble, water bubble, water bubble, water bubble. So water bubble will be blue. So if you are in the water dominated, you will see the oil bubble. If you are in oil dominated, you see water bubbles. So the other way. Yeah. So the threshold is there. It can be adjusted automatic depending on the tool type. It can be set or it can be automatic. Then at the end, For example, you're measuring maybe 100 millisecond. You're measuring in 100 millisecond, you have some different signals here. So up and down. So you count the total time by the blue period divided by the total t, then this is your holdup of water because it's blue. Collecting all the blue areas in the total time frame, say 100 millisecond. So every 100 millisecond you acquire every 100 millisecond. So you have a holdup every millisecond. And that's the holdup water. So of course, 1 minus this is the holdup oil. And you can have the bubble count. The bubble count, you can see this one is 2, 3 bubble, 4 bubbles. So you can see the number of the transition here is bubbles. So the transition, yeah, maybe up and down. So the total transition divided by 2 will be the bubble count, the number of bubbles. So you have the bubble count and you have the water holder. So you have to output for each probe. For example, you have depth, you have 4 probe. So you have 4 water holder, 4 bubble counts. So they're coming from the tool itself, from the probes. Yeah. So this one, TFB is bubble count, TFH is soda for each different probes. Okay. TFBM is the average, TFXM is the average, the mean value. And filter average. Usually we don't use that one. We use the individual because we'll see which one is not good, for example, because the average is just use all of them. If there are one of them not working, the mean value will not be good. D1RP is position probe number 1 to vertical. So if you have this is the 1, 2. If you have 2 tools, because it's only 4 probes, right? If you want to be 8 like this, so the more coverage, you'll be having the second depth or second flow view. You have the D1RP2, which is the position of the second depth, second position, the second tool. That's the thing, yeah. And then we have optical. It's refractive index, it's fiber optic or plastic, whatever. The gas will be bouncing back all 100%. Water will be dumped, will be reduced. Oil will be all reduced, so there is no reflecting. So you might see oil, water, and air or gas. So you might have 3 different condition refractive index, and then you can use for 3 base holdup. Yeah, it's based on the refractive index. So you can see that the principle is easy. And the tool itself is very, very small. It's really like a needle. So imagine if you have 4 needle in 5-inch casing, so you are not covering quite a lot. That's why the correction is quite high. So it's something like this. You have photodiode send the lamp or through the optical fiber, so send light and move back to the light source, and then photodiode is the sensor of the light, the reflective light. So it's simple like this. And open film also use the same thing. So it's for 3-phase holdup. It can use for 3-phase as well. The same principle. So remember, on the electric, you have only 2 steps. Two conditions: conductive, non-conductive. This one you have 3 conditions. You have 3 conditions. You have gas, you have water, you have oil. The refractive index, you can see back to this one here. This is high reflective, this oil, middle water, bottom one oil. So it's similar. So you have something like this. Yeah. So baseline may be water. So if you dominate it by water, if you have some gas bubbles, you might see the voltage increase. But if you see the oil bubble, you'll see the decrease. So if your base is dominated phase is water. What happens if your dominated phase is gas? So mostly gas, and if the voltage drop above the water, then it should be water. But if the drop of the droplet is below the water, then it should be oil. It's oil bubble or gas or water bubble. Yeah, in the gas. If you are in the oil dominated, you can see the bubbles of water or gas depending on the changing of the voltage. So you have the threshold here, right? So if the drop is only this, then should be water. But if the drop is up to here, so this be oil. So you have three different conditions, three different voltage. Yeah, so you might see this one. So that's the same thing, you might have the gas holder and double count. You have GSB, GSH, or something like this, and then we come to capacitance holder. So principle is all about this, not the same as the resistance, but this capacitance. So you might have this three-phase condition, just correction. So the reading is 0, 0.2, and 1. And cap is normalized capacitance. 0 is gas, 0.2 is oil, 1 is water. So that's the three condition. And you might see different, if you have between oil and gas, sorry, oil and water, you will fall on this blue line. If you are in the gas and oil, you will fall in this green line. If you are gas with water, you will be on the yellow line. In between is in the middle. It's a three details. So it's something like that. It will be calculated automatically. As mini spinner, so this is the set. You can see the set is something like this. So that you have some dot, which is the magnet, and you have a Hall effect switch here. So when the magnet passing through, it switch on, off, on, off, on, off. So the number of rotation will be as a number of signals. So you will be calculating the signals, calculating as the CPS to get the RPS. Depending on the number of magnet, it's only one sensor. Yeah, this is in the different position, circular position. But if you look at the FSI, it's in the vertical position. So they are different. They are different. You can see this one. You have pi and fast tool. FSI is number C1. It's only one arm. The idea of the tool is to 0.18. It should be heavier than the arm. So the arm should be moving vertical. The map is a post spring type of arm, so you can rotate. And you have the pi. This is the new breaker switch. So one arm can have three sensors. You have spinner, you have optical, you have electric. So you have, and also you have 6 arms. Because the 6 arm you can adjust maybe 3 arms on the outer ring or outer circle, the 3 arms on the inner circle. So you can have more coverage if you are dealing with the bigger pipe. So you can have three at the outer one, maybe the other one in the center. So you have a 2 circle, for example. So the coverage on the outer close to the wall and the 3 of them closer to the inner, closer to the center. So you have more coverage because the set or whatever is close to the wall. So we are missing the middle one. And the open field is the fast tool. So yeah, this is the new tool. This is only 1 meter length. So you have the Doppler sensor, you have temperature, you have pressure. Doppler, you have 8 segments, and you have battery for memory, etc. This one is modular, so in one arm you can replace the sensor, either spinner or electric or optical. So
Can change.
can change.
Oh.
Can change. Yeah, there are several new tools which will be almost the same. The axial is the same like this, so only one arm. So the processing of the multi-probe. Yeah, you can have something like this. So you slice the pipe, it's horizontal, you slice one pipe, so you see all the dots, small dots are the capacitance, for example. Then you make a 2D mapping. You make a 2D mapping, something like this. Yeah. So you can see this one. It's only one slice. The slice depend on the number of sampling. So you put this one, yeah, like this. It's a vertical segment. So then you might try to have some interpolation between points. So then the area below that line is water water on that slice, on that depth. So 1 minus water holdup is oil holdup. So you can see this one. So you know the holdup based on the capacitance array. Then we like to have the velocity mapping as well. This is just for the gap or right or both. Then you can see. So error minimalization between between the dot and the line. So you can have linear is straight line between point. Polynomial, so you get a smoother transition. It's not very safe, something like smoother line. Proprietary is the slow machine one. Yeah. So you can have single pass or step or several pass. Like we already seen, there are 2 pass in the horizontal. So you can combine. If the tool or if the well condition is the same, we can combine, right? It's like you have 12 times 2. It's like you have 24 capacitance flow because you combine. As long as the well condition is the same and the tool has rotated. Because if the tool is not rotating, it will be keeping the same position, so it's not used to get the two combined. User constraint, yeah, for example, I have only water and oil, I don't have gas, so I just put yg equals 0, any other constraint. So that's the holdup. So we do that again. Okay, this is the integral, just the integral of from minus L to R. Yeah, this is the area of the pipe. This is the difference of the segments. The number of segments is dz. So in Emerald, we have, I think it's 50 segments, horizontal segments. So you just integral of all the segments. And you do also for velocity. You have 6 set. You have this 3 2D mapping as well, the same like that. So we have this profile. So at the top, oil, you have higher speed. In the water, you have lower speed. And then we combine those two. So you know this segment, the bottom segment hold up, you know the velocity times hold up is the Q on that segment. So you do one by one for each segment, you accumulate, you integral of the Q of the segment. So you know the segment or the total area of water or velocity is a keyword. No need for correlation. So it's something like this, it's integral of hold up and velocity per segment, area of the segment. So it's done.
Is this like more accurate than
No.
no?
It's more confusing, yes. More accurate, yes, in term, if it is in segregated laminated flow regime, because we know the light phase, heavy phase, right? That's better. But you can see the reading is noisy. It's fluctuating, so it's not that easy. Like we see before, we can just match the green to the red. It's very easy.
Mm.
But this one, Q water, Q oil. So you believe on that one or you believe on this one? So there's another question. So we like to, we like to have another information to choose something like this. You believe that or you believe more on that one.
Mm.
So there's something you might need to know later on with what you call it, the trajectory. So if your trajectory is less than 90 degree, so you might believe more on the Q oil. But if you are going downhill, okay, sorry, so if you're going downhill, your water holdup will be smaller, so occupied by the oil holdup. So if you are going downhill, you might believe more on the oil. If you're going uphill, you might believe more on the water. So you need to know the grade, the changing of the trajectory. Yeah. In theory, it's good, but in reality, it's something like this. And then you try to make the model. Yeah. So you have to hold up oil, but we looking at only those two, right? Because we already have the Q water, Q oil. Yeah, if you global regulation, multi-phase. So it's something like this then. So we try to match. Yeah, we do some SSD or I don't know ICDs. That is ICDs there, so you might see the different ICDs position. Then you might try to make sense of it. Yeah, sometimes you see this one. You might try to get it, but it's not as smooth as we see from the conventional. Yeah, it's a lot more fluctuation. Okay, so that's the end is the same. Yeah, the result is similar, few different phase. But the data there is calculated using multi-clock tools. So we have the same thing like this, we already same. Yeah. Now we do have a recirculation of ADF. So I think I've explained before, right? So if you have oil or gas on the upper side, the water will be circulating back at the low side. And when the spinner is there, it's reading the circulation of heavy phase, which is negative. So we call it apparent downflow, not real downflow. So the light phase is not seen by the spinner. So the requirement of ADF is deviated. It can be as small as 10 degrees. Multi-phase, at least two phase. Low fluid velocity. If it is high velocity, then both phase are moving up. Because it's low velocity, so the heavy phase is just recirculating back down. Because the light phase doesn't have enough energy to read all the heavy phase. Something like this. So if you look at the spinner there, it's negative, right? So you might see this is the casing, and in the tubing, you have vibration in the casing, you have some negative. But in the tubing, you have some positive. So you might have something like this one maybe is producing down, and this is negative, right? So if this one is producing, going into the bottom in the casing.
一下可以过那个parent level.
Yes. Hmm? Yeah.
We go that is
Yes.
可以下个
Yes, apparent downflow. It's not the real downflow because the spinner is reading the heavy phase, which is all water. Water circulating back down, it's not water moving down. Yeah, so that's why we call it ADF, apparent, not real. And expected in the interface of the different, yes, there are different phases. IPR. So in order to check whether real cross flow, real downflow or not, IPR. Or you check with the shut-in. If it is real downflow, then in the shut-in you will be seeing more downflow. Yeah. If not, then this is just APM. So you look at the shut-in or material or different phase. So you make,
What is IPR?
what's that?
IPR.
Inflow performance relationship is SIP. It's the SIP. Inflow performance relationship. So between Q divided by delta P is productivity index. Q divided by delta P. Yeah. So how to look at whether IDF or not? Yeah, we need to look for other rates, other surveys, look at your RBR, or yeah, you can try to make sense this one. Because if you know, if the water is moving back down here, so I would rather have the water level will be at the bottom. Because you have all water up to here. If water is pushing back into bottom, then the water level should be dropped. So we have the calculation apparent downflow in emerald. So it's just the approach. Maybe it's not correct. So VSL is velocity superficial light. QL divided by the area. Constant slip at velocity, light phase hold up. Heavy phase hold up not moving. So yeah, we don't use spinner. Water velocity not moving. Light phase based on the correlation. So liquid gas using Doppler, the liquid using ADT. So that's the one. We don't know what the C is, yeah? It's a constant, so we don't know. VS we can get from correlation. This one you can get hold up from capacitor, density, DPDC. That's okay. But when we need to look at the, for example, capacitance I'm looking at in the tool. So it's not representing the hold up in the pipe. Yeah, DPDC may be better. FDR is just measuring in the tool. So it's not measuring all. So you might be missing the light phase at the top. So be careful on that. The holdup should be representative in the pipe because this one is casing, it's a big pipe. So the holdup may be in the middle, just looking at the heavy phase. So maybe 100% water. But actually you have missing the top part, which is light phase. Yeah. Limitation, heavy phase can be moving. So the assumption here, heavy phase is not moving. Of course, the correlation depending, we just choose Doppler or ABB. The hold up to representative. So whether that one is representative or the fluid in the pipe or not. Because most of the two are reading only inside the tube. And PVT, yes, of course, depending on the PVT, the calculation, P and T for the slippage.
Yes, in that study, what is the basic information you identify that is the zone at the bottom still continuing from
This one,
here?
because it's getting less. If it is moving more to the left, it means you have more light phase coming in. So that's why you put this one is as a production. If you just going like this and straight, so you just put that one in, because it's gradual there, and then steady. So between the gradual is like an inflow, so you have perforation. Yeah, you start changing the spinner because you might have some additional circulation because you have additional light phase coming in. Yeah, it can be because it cannot be more circulation if there is no additional. Yeah.
Not really makes sense. Yeah.
Hmm?
Not really makes sense.
But why you have decreasing?
Yeah, decreasing. Yeah, we observe that is there some echo that the flow back, but to the upside, we observe that is the
Because
will inflow.
we don't have the picture. Yeah, because when you, I don't have the picture. This one here. If you have more oil, you have will be the volume or the space will be displaced by more oil, so the water will be moving back more because the volume is occupied more by the oil. So displaced water will move back more. So that's why you have a more negative because you have more oil.
It's that the basic information that is the volume of the waters, the volume of the light phase on the top.
Yeah.
Equivalent with the equal to the volume of the
Yes.
volume of the
Yes.
phase.
Yes. If you have another inflow, it means the volume of oil is increasing. Right? Then you might have some water displaced by the oil, more water displaced by the oil because the volume is an on ID, right? So it cannot be bigger. So if you have more water and more oil, then the water will be decreasing. And because it's moving up, then it's more moving down of the water. Well, we'll see. Yeah. Okay, so this one is the Schlumberger FSR. So this is the tool. Yeah. And you might see this one like here. At the top, you have, oh, this is the spinners. Yeah. This is FSI spinner. 1, 2, 3, 4, 5. Number 3 is contact. So it's the spinner. But if you are in IDF, you can see in the water, you have a negative spinner. spinner is negative and spinner is positive, you have more oil. So you have more oil, you have more positive, you have less negative, more negative. So you might see the difference. This one, all the water is moving up, but in this case, the water is circulating down. The yellow is the spinner. Okay. So you might see something like this. Then we put the water and we display. So we do the water shut-off equation, something like this. Okay, I guess we're done with this theory.